Hello, my name is Evan Benoit and I'm a student at the University of Utah. Today I'll be presenting on inversion techniques for SSTDR analysis and how that applies to remote health monitoring for PV systems. So shown here is a very large solar farm. It's in California, produces about a half a gigawatt of power, and as you can see there's thousands and thousands of solar panels. A big concern with these large solar farms are what happens if a fault occurs. Faults can happen in panels and they can happen in interconnecting cabling, which makes this kind of like finding a needle in a haystack if you have to go look for a fault. So we're proposing that we use spread spectrum time domain reflectometry to be used for remote monitoring of these solar farms. Spread spectrum time domain reflectometry, or SSTDR, is already being used in many industries. One of them is the aircraft industry to monitor the many kilometers of aircraft wiring tucked behind the bulkheads of the airplane. It's also used in precision agriculture, railway systems, and nuclear power plants. So what is SSTDR? SSTDR is similar to radar, but for electrical wires. Here we send an incident pulse into a transmission line and listen for the reflected pulse to come back. We analyze the difference between the incident and reflected pulse to figure out what we ran into, just like what happens with the radar signature. Our SSTDR signal is constructed by using a PN code generator and a square wave generator, and then modulating the output of the two of those together. That modulated square wave is then launched down the transmission line, where it reflects off of any impedance mismatches and returns back to the source. Before launching our signal, though, we record a copy of our incident signal, and then we record a copy of our reflected signal so that we can cross-correlate the two of them together. This little video I'm about to show you shows what happens when we cross-correlate. So I want you to see the incident signal. There's a little red dot in the center, and the reflected signal, there's a red dot on the far left. And the line at the bottom is our cross-correlated signal. So as we're time-stepping the reflected signal through our incident signal, we're building the SSTDR response that's shown down there at the bottom. This response here is characteristic of an open circuit. The open circuit response is unique because it's a complete reflection of our incident signal. Another one would be a short circuit, which is a complete inverted reflection of our incident signal. A matched load, which would be no reflection at all of our incident signal. And then a mismatched, which is somewhere in between an open circuit and a short circuit. I want to highlight the open circuit, short circuit, and the matched condition. So what are these actually telling us about the SSTDR analysis? They're actually giving us the reflection coefficient. Well, what is the reflection coefficient? It's the ratio between the impedance of the transmission line and the impedance of the load. In the open circuit case, the load impedance is infinity. In the short circuit case, the load impedance is 0. And when the matched impedance, the load impedance equals that of the transmission line. So I'm going to highlight the open circuit and short circuit and move on. The open circuit and short circuit are unique because there are upper and lower bounds of our reflection coefficient. This means that a reflection signature from any resistance or impedance that's between infinity and 0 will lie somewhere between our characteristic open circuit and characteristic short circuit SSTDR response. Next, I'm going to show what happens when we vary the resistance from a high impedance down to a low impedance. So on the right, you see an open circuit and a short circuit. Those are characteristic of SSTDR. Then we drop down to 750 ohms. And on the way down, you can see that the reflection just changes in amplitude. It doesn't actually change anywhere else in the reflection coefficient. Not all SSTDR responses only result in amplitude changes. For example, if we look at a solar panel with the SSTDR, the reflected signal is skewed. This skew is due to a frequency dependence from the capacitive nature of solar panels. The SSTDR response is skewed by frequency-dependent components, such as capacitors or inductors. And since the SSTDR signal is a broadband signal, each frequency of the incident signal results in a slightly different reflection coefficient. This slight difference in reflection coefficient over the whole frequency band of the incident signal results in the SSTDR signal to be skewed. So shown here is a comparison of a 50 picofarad SSTDR measurement and a range of resistances discussed earlier. So conversely to the resistive load changing from an open circuit to a short circuit due to decreasing resistance, capacitive loads will transition from an open circuit to a short circuit with increasing capacitance. However, inductive loads do behave similar to resistors and transition from short circuit to open circuit with increasing inductance. So, we know that PV panels are frequency dependent, which causes SSTDR response to skew due to the frequency dispersion, and the presence of skew depends on the type of load encountered by the SSTDR signal. Lastly, the upper and lower bounds of the reflection coefficient are 1 and -1 respectively. But how have we applied this information to PV health monitoring? We've developed peak detection algorithms capable of tracking changes in the SSTDR response peaks, which is indicative of a change in the impedance of a load. We have developed dictionary matching algorithms to aid in fault detection, and we have used machine learning algorithms to extract key characteristics of factors affecting the SSTDR response. One of our peak detection algorithms monitors exactly what we've been viewing during this presentation, the center peak of the SSTDR response. We've identified 3 peaks, A, B, and C. These all change in magnitude and location within each other depending on the impedance mismatch encountered by the SSTDR signal. Tracking the peaks of the inductors and capacitors through the range of open circuit to short circuit highlights regions of detectability. However, capacitor values near the upper bound appear to be very similar to an open circuit response and are extremely hard to identify. Likewise, capacitors of high value, which are easily mistaken for short circuit responses. But the good news is that we have a relatively large window of detectable capacitances, which is shown by the starred section, the teal starred section between capacitor 1 and capacitor 2. We've also identified the same response for inductive loads. A major benefit of using the SSTDR comes from our ability to modulate the PN code with a higher or lower square wave frequency to shift our windows of detectability to the left or the right depending on what we're trying to measure. This effect exploits the frequency dependence of the load in our favor. Our dictionary matching algorithm takes a large sample of simulated capacitances and stores them in a matrix. The short video that I'm about to show you shows a sample of some of the capacitor responses that are stored in the dictionary matrix. The dictionary matrix stores each of these capacitor responses in the columns where each response is made up of n sample points. As you can see, the capacitance is moving from an open circuit to a short circuit. All of those capacitor values are stored in the dictionary to then be reviewed later to pull out the measured capacitance. The measured response, shown in red, is correlated with each column in the capacitor signature dictionary to produce a correlation coefficient. The correlation coefficient is a measure of similarity between the SSTDR measurement and the stored responses in the dictionary. Correlation coefficients greater than 0.99 are shown in the figure on the left and indicate how accurately we can identify the capacitors in the SSTDR measurement. Similar to the window of detectability from the peak detection algorithms, dictionary matching is also plagued by difficult analysis near the bounds of the reflection coefficient. Shown here, the 2 test capacitors highlighted in blue are outside the window of detectability and appear as open circuit responses to the algorithm. However, the rest of the test capacitors are detectable and lie well within the region of detectable impedance. Again, we're able to shift these detectable windows by changing our modulation frequency of our incident signal as desired for our load. Our dictionary learning algorithm utilizes a KSPD machine learning technique to aid in fault detection. But first, to use this method, we had to collect 2 training data sets. One training set lasted for about 48 hours of continuous measurement and resulted in about 1.7 million recorded reflections. The second lasted for about 6 days and produced 7.6 million reflection responses. During both of these data sets, manipulations to the measurement system were performed by connecting and disconnecting the MC4 connectors between the PV panels, by systematically shading and unshading the PV panels, and by allowing the system to be bathed in full sunlight as well as recording reflections during the night. The data sets were trimmed in size by passing every 1,000th sample to the KSVD algorithm. This was done to minimize computation for the simulation. Constraints were placed on the KSVD algorithm to produce only 30 atoms with a sparsity of 4. This means the KSVD algorithm decomposed the training data set into 30 linearly independent atoms to be stored as a dictionary, where a maximum of 4 atoms would be used to reconstruct the reflections in the training data set. The results of this are shown in the figure on the left, the green figure. The 30 different atoms are stored in the rows, and the reflection measurements are reconstructed using the atoms in the columns. You can see the training data set samples are going from 0 to about 7,700. Highlighted in this slide is the one atom, atom 4, that had the highest correlation value, meaning it was used most frequently when reconstructing the training data set. In this particular example, atom 4 is strongly correlated with the daytime SSTDR response. The 4 atoms shown below the daytime SSTDR response are used to reconstruct the daytime signature of the PV panel system. This was an unsupervised algorithm, and it took operator intuition to identify this response as a daytime measurement. The same occurs with atom 7 during the nighttime SSTDR measurements. Another algorithm was used but not shown. This was called DKSVD. This is very similar to KSVD, but with the added complexity of fault characterization through class identification, meaning this method could be considered a supervised dictionary learning and greatly increases the ability of the SSTDR to be used in PV panel fault detection. The unsupervised method can actually classify and characterize faults based on the training data set that you feed it, which greatly improves the SSTDR capabilities. Our peak detection algorithms are excellent for preliminary understanding of SSTDR reflections and how they change based on the load encountered by the incident SSTDR signal. The dictionary matching algorithms are excellent for detecting specific types of faults that can be stored in a known dictionary. And our dictionary learning algorithm is robust in analyzing large data sets and establishing dictionary of faults to be used on other systems. Our peak detection algorithms are limited to cursory inspection of SSTDR reflections and give basic characteristics of reflections from faults. Furthermore, fault detection using this method is limited by bandwidth of the SSTDR signal. Dictionary matching is limited to building the lookup dictionary by brute force and can be computationally expensive, depending on the size and complexity of the dictionary needed. Additionally, this method only works with dictionaries of measured or simulated faults, and it also is affected by the bandwidth of the SSTDR signal. Dictionary learning requires large data sets to train the SVD algorithms, and the faults in the data set must be known to properly train the algorithm. Feel free to visit our publication website for more detail on the topics discussed today. Thank you very much for your attention.